right, guys. Thank you very much.
Thank you.
And I asked our next speaker to come up. And our next talk will be on using Trio, Juniper Networks Programmable Chipset for emerging in-network application. And the presentation will be given by Mingram Yang from MIT. And Mingram is a second-year PhD student at MIT, working with Professor Manya Gobadi, and her research interests include programmable switches and data center network, exactly the topic of her presentation. So please, take it from here.
Thanks, Anya, for the introduction. Hello, everyone. My name is Mingran, a PhD student at MIT with Professor Manya Gobadi. Today, I am going to talk about our work using Trio, Juniper Networks Programmable Chipset for emerging in-network applications. This is a joint work between MIT and Juniper Networks. Data-intensive applications, such as machine learning, databases, storage, and data analytics, are the foundation of today's online services. With the gradual slowdown of Moore's law, hardware accelerators are struggling to meet the performance demands of emerging cloud applications. In addition, the amount of memory and computation that can fit in a single server is limited. This results in our need for efficient distributed systems for data-intensive applications. The availability of programmable switches, such as Intel's Tofino, has created opportunities for in-network computing to accelerate data-intensive applications, such as caching, database query processing, and machine learning training. The key idea of in-network computing is to leverage the switch's unique vantage point to perform part of the computation directly inside the network, thereby reducing latency and improving performance. Let's take a deeper look into one of the representative applications, machine learning training. In data parallel distributed machine learning, the deep neural network is replicated across multiple servers. And each server processes a small subset of the entire training dataset. At every iteration, the servers will synchronize their model parameters by exchanging and aggregating their gradients to ensure convergence. This step is called all-reduce. One challenge with the all-reduce step is it puts significant pressure on the network fabric because the entire set of model gradients must be exchanged many times during the training process. Recent work, such as SwitchML and ATP, has proposed the idea of in-network aggregation to accelerate distributed machine learning training. In the rest of my talk, I will use in-network aggregation as a running example. The key idea of in-network aggregation is to use the programmable switch to perform the gradient aggregation instead of at end hosts. In this way, the training performance with heavy is accelerated for heavy communication jobs. Our results find out that the presence of stragglers imposes a deployment challenge for in-network aggregation for distributed machine learning training. The straggler problem is very common in clusters where different servers often experience uncorrelated performance jitters due to congestion, load imbalance, or garbage collection. When this happens, other servers must wait for the slowest server. The straggler problem has been studied extensively in the system and networking community. However, there hasn't been much attention to straggler mitigation for in-network computing applications. Why is this? The reason is enabling efficient in-network straggler mitigation in Tofino switches is challenging. To perform in-network straggler mitigation, the switch needs to perform timer-based operations, such as checking whether a straggler event has occurred or not, and sending notification packet to servers periodically. This is quite challenging in Tofino switches because it requires frequent interaction between the data plane and the control plane. As a result, today's Tofino-based solutions have no in-network straggler mitigation implemented, and all the servers must always wait for the slowest server when straggler event happens. In this talk, I will discuss TrioML, our proposed systems for efficient in-network straggler mitigation. In particular, we can achieve 1.8 times faster training time for machine learning jobs by leveraging Juniper Networks' programmable chipset. In the next part of my talk, I will first give an overview on Juniper Networks' chipset. Then I will discuss TrioML, our proposed in-network straggler mitigation for distributed machine learning training. Finally, I will talk about our evaluation results. In Tofino switches, the central packet processing element is pipeline. All packets must traverse through the same set of pipeline stages, independent of the application. Trio is a programmable chipset used in Juniper Networks routers and switches for over a decade. The architecture of Trio is fundamentally different from that of Tofino. It has thread-based architecture, and the central packet processing element is packet forwarding engine. For an incoming packet to Trio-based programmable switch, after it enters ingress packet forwarding engine, it will be processed by one of the available threads. Then it will be sent to the egress packet forwarding engine and will be processed by another available thread. After the process is completed, the packet will be sent out. When multiple packets arrive, these packets are processed independently using thousands of threads inside Trio. Since different packets do not necessarily flow through the same set of physical paths on the chip, Trio gracefully handles non-homogeneous packet processing rates, whereas in Tofino, only line rate processing is supported. With the Trio architecture in mind, I will then discuss TrioML, our proposed in-network straggler mitigation for distributed machine learning training. To build efficient in-network straggler mitigation technique, we need in-network straggler detection, which enables the switch to efficiently detect straggler events. We also need in-network straggler recovery, which enables the switch to gracefully serve the job without waiting for stragglers. In-network straggler detection requires timer-based operations based on user-defined timeout. And in-network straggler recovery requires a lightweight mechanism in the switch to proceed the computation. Our system, TrioML, addresses both challenges using Trio's threads. Let's first take a look on in-network straggler detection. As a reminder, back to our running example, in-network aggregation for distributed machine learning training, the server will send the gradients every training iteration, and the switch will perform the gradient aggregation and send back the results to all the servers. TrioML creates a new gradient record when it receives a new packet from the server. In normal cases without any straggler, the gradient record contains gradients from server 1, 2, 3, 4. After TrioML receives gradients from all the servers, it completes the computation and sends back the aggregation result. To build an efficient in-network straggler detection, our goal is to detect non-responsive servers with delta millisecond timeout interval, where delta is a user-defined parameter. In the straggler event case, suppose server 4 is a straggler. The gradient record only contains gradients from server 1, 2, and 3. One naive approach to detect the straggler is, as soon as a new packet arrives, the switch launches a new thread and starts a new timer to keep track of non-responsive servers. The problem with the naive approach is it couples the start of timeout threads with the arrival of new packets. The switch will need to create one thread per packet and is therefore not scalable for very large machine learning models. To bump the number of timeout threads needed, TrillML's approach is to decouple the start of timeout threads with the packet arrival. In our design of TrillML, we divide the gradient records into n groups, and each group is scanned by one of the threads. We also add a specific recently referenced flag to each gradient record. This flag is set to 0 when the gradient record is first created. Every delta timeout interval, TrillML launches n threads to scan the gradient records. If the recently referenced flag is previously set to 0, the threads will set this flag to 1. After another delta timeout interval, TrillML launches n threads to scan the gradient records again. If the recently referenced flag is 1, then the gradient records time out, and the straggler is detected by the threads. With this approach, TrillML guarantees a straggler detection within delta to 2 delta timeout interval. After the straggler is detected, we need a mechanism to perform in-network straggler recovery. TrillML's approach to recover from straggler is to send partial aggregation results to all the servers. Prior results show that partial aggregation can achieve comparable convergence performance. With this approach, non-straggler servers can continue to make progress without waiting for the straggler for a long time. In addition, TrillML keeps updating the straggler to ensure the machine learning model is consistent among all the servers. In the next part, I will talk about our evaluation results. To evaluate training performance, we perform training tasks on a real-world testbed, including 1 Tofino switch, 1 Juniper Networks router, and 6 servers. We compare our solution, TrillML, to Tofino-based in-network aggregation proposal, SwitchML, and also an ideal environment where no straggler is added. To evaluate the performance when straggler exists in the cluster, we followed prior work on straggler generation pattern. Namely, we set 3 possible delay points per training iteration. One server slows down at each delay point with given probability p, and the delay time will be uniformly randomly chosen between half to 2 times of the typical iteration time. The first result I would like to talk about is the impact of straggling probability on training iteration time. We train VGG11 model on ImageNet dataset. On x-axis, we sweep through different straggling probabilities, and on the y-axis, we show the training iteration time. The red line shows the result for SwitchML. As the straggling probability increases, SwitchML's training iteration time also increases because the switch is not able to recover from stragglers and therefore need to wait for straggler before generating any aggregation result. The blue line is TrillML's result, and the green line is the ideal case. With the straggler probability increasing, the TrillML line stays close to the ideal case. This is because TrillML mitigates the effect of stragglers with its in-network straggler mitigation technique. When straggling probability p equals to 16%, TrillML achieves 1.8 times faster training iteration time compared to SwitchML. The second result is the time to accuracy improvement when straggling probability p equals to 16%. On the x-axis, we show the training time, and on the y-axis, we show the validation accuracy. The red line shows the SwitchML's training time result, and the blue line is TrillML's result. With a moderate rate of stragglers, TrillML achieves faster time to accuracy time and achieves 1.6 times speedup compared to SwitchML. We also observe similar gains for ResNet 50 and DenseNet 161. To conclude, Stragglers impose a deployment challenge for in-network computing solutions. In this case, we propose TrioML, a novel in-network straggler mitigation system using Juniper Networks' thread-based programmable chipset. And TrioML outperforms today's in-network aggregation solution by up to 1.8 times. That's all for my presentation. Thank you for listening, and I'm happy to take any questions.
All right, we have our first question here, please.
Thank you for your great presentation. So my question is divided into two. The first one is, what are you doing when the deployment of the machines, the servers, are not under the same top of the rack where you have a hierarchy? That's the first one. And what continues to that, what will happen if you have a switch straggler? When you have a higher hierarchy, now the switch is struggling in order to pass this information, and it will cause a much higher error rate because now you have more missing vectors.
Okay, thank you for the question. So for the first question, we have hierarchical deployment. If we have multiple servers that cannot be connected to a single router, we can connect them in a hierarchical way. Basically, we have first layer aggregator, and also we have top layer aggregator. So that's the first question. So for the second question, you are asking, what if the switch becomes a straggler? Is that your
Exactly. You have a straggler, and then that switch becomes a straggler because now it won't pass the information to the next hierarchy, right? Or it has a load, and therefore it didn't pass the information to the higher hierarchy yet.
I see.
So the error will be much higher because you have more missing vectors.
I see. So basically, in our evaluation, we don't see a switch becomes a straggling. Also, there are no prior research shows that the switch can be slowed down during the runtime. But if it happens, we can also, like if we have a hierarchy of switches, we can also deploy a straggler mitigation technique on other switches. So if all the switches are all doing the straggler mitigation technique, this issue can be solved.
Let me actually jump in there. What happens if you have a packet loss of one of your aggregation packets?
Packet loss?
Packet loss.
So in our experiment, so packet loss, do you mean it's injected by the straggler or by?
No, one of your aggregation packets just got dropped.
I see, I see. So basically, if the packet is getting dropped, it will be resent by the server, and it will be reprocessed by the switch. So currently, our approach doesn't have this mechanism implemented, but it's easily implemented in our approach.
Hey, Jun Kim from Princeton. I was just wondering, like, on the switch, do you just wait for the straggler, or do you do anything more than just waiting? Like, do you like send anything to the server for like send it faster, or like do you measure anything? Why is it straggling, or do you just wait?
I see. Yeah, that's a good point. So currently in our design, the switch is periodically scanning the gradient records to detect whether a straggler has occurred or not. So if the straggler is detected, we are releasing the partial aggregation results to all the servers. We are also considering a more general straggler mitigation framework using the timer threads. So in that case, we can deploy other mechanisms to notify the servers if the straggler is happening, and also we can do more analysis on what is causing the straggling event.
Jen
Rexford from Princeton, really nice talk. I wanted to try to better understand how much of the gain you're getting is from the straggler mitigation and how much of it's coming from the switch architecture. And so I'm curious if you imagined porting something like TrioML to something like Tofino with control plane straggler mitigation, or relying on recirculation in the switch to do it. So obviously it would not be as good as what the Juniper chipset would do, but I'm trying to understand how much of the gain you're getting is from doing straggler mitigation at all, and how much of it's coming from using a switch that's better suited to doing it.
I see.
Does that make sense?
Oh, yeah.
Just curious.
Thank you for the question. Yeah, it's a really good point. So currently, we see the main improvement is based on straggler mitigation technique. It's when we have the results showing when straggler probability is 0%, true ML actually acts really close to switch ML. So basically, the improvement is mainly based on the straggler mitigation technique. For porting something like true ML's mechanism in Tofino switch, I have actually tried this when I began this project, and I find it's not straightforward and challenging because it incorporates many control plane operations, and it induces a lot of unknown delays because of the interaction between the data plane and control plane. And so basically, I think if we can have something similar in the Tofino switch, it will be good, but for now, true ML still outperforms switch ML because the straggler mitigation technique. And we also want to open up
Two more quick questions, please.
Oh, sorry.
Thank you. Sarat Aslan from Stanford University. Great talk. It's great to hear about different programmable switches. So could you please talk a little bit more about the memory interactions with the threads and the shared memory in the trio switches, especially for state storage and manipulations with different threads? What kind of scalability is there?
Okay, guys, you take that one offline because that will require much more time. Short question there, please.
Oh, yeah, so we have that in the paper. You can check for more information in the paper.
Thank you.
Section 3.
Jason Lei from Purdue University here. Just quick question. What happens to the straggler packets like from a straggling router? So if everything else gets partially aggregated, does the straggler end up getting aggregated later, or is it just dropped entirely?
So basically, in our current design, the straggler will get the aggregated packets, but I think this mechanism also applies to if the straggler just dropped the packet at all, then it will just resume when it comes back.
All right, thank you.